Alrighty, guys, how we doing? It's a small class we have on Fridays, so let me just start by writing down all the plan for next week. Right, so Monday, the TA has office hours from 4 to 5:20, and then Tuesday, that'll be me. I'll have office hours from 2 to 3, and then Wednesday, we'll have the second midterm. And then on Friday, we will look at the solution. It's going to be a little bit tricky getting the exams back to you guys. So my best suggestion so far is to have a view your exam on Zoom. So I'll set up a time slot where each one of you, one at a time, I'll open up your exam, and then you can take pictures of it, and then you will have it. And then if there are any questions or comments, then there'll be another time where you can ask about it. But I want to give you need to have your exams back before the final. And then the exam is on Wednesday, the December 22nd, and this is from 12 to 3 p.m. and it's in our room B219. Any questions about the last week of class that's coming up next week? All right, so here the focus, this is on the second part, and this is all material. Okay, so that's what we're going to be doing for the rest of the semester, and what I had in mind for today was to go over some of the sample problems that I uploaded. There was one thing that came up in the office hours yesterday, so maybe I should start by discussing that. So in yesterday's office hours, there were a few questions about these continuous bijections. So from yesterday's office hours, and this was related to homework 10, we were interested in for example, if you looked at a circle, like could you find a map that would map in a continuous and bijection form into, say, the interval 0 to 1, something like that. And so the hint was, right, so here we have, so this set here, right, those are those x's in R2 such that they are of length 1, right, and it maps over into the interval 0 to 1. And so can you find, does they exist like a continuous bijection? Does there exist, this is the question, right? Does there exist such a thing that takes you from this circle over into this open interval? Right, and so the hint that was in the homework was, well, so you follow the hint. Follow the hint, you say, well, let me take a point. Let me take a point out. Pick a point on the circle, say, and so you could pick you pick this one here, right? And then the rest is there. So this point here, this is 1.0. Right, so then your function f, now we're moving this 1 point, right? So where does it map? It's going to map over here in that interval, and it's going to reach all the points except one. There's going to be a hole here. So this is going to be, that point here is going to be this f of 1/0. And so you could ask, is this possible? Right. So if there exists such an f here, then you can also map these two. So is that possible? And what do you guys say? So this here is those x's in R2 such that, well, it's those x's in R2 except for that 1 point, such that you have norm 1. And then this set over here, this is going to be 0, 1 less that one particular point. Does there exist a continuous function that will take you from this set here to that set here? Aya says no on, and why is that, Aya? Why is that, Aya? That's right. Because this one here is connected, and this one here is not. So you can see it's, if you get this, you can imagine how one would go about creating midterms and finals. You do a variation of this. So let's try to do a variation. If so here's another example. So let's consider circle, but fill it out. So those x's in R2 such that the x's norm is less than or equal to 1. Again, where should we map it? Well, why don't we try to map it into the circle? Does there exist a continuous projection? What do you guys say now? Alex says no. And Alex, do you have a, let me hear your reason. Let's try to remove a point. If you remove 2 points, that's right. Very nice. So you remove 2 points now. Very good, Alex. Awesome. Remove 2 points. So you have your circle. And you're going to puncture 2 holes in it. And then we have this. Right, so then this is going to get mapped over into something. There's a hole here, a hole here. This one here is still connected. This one here is not connected. Okay, does that make sense to you guys? Are we good on this? So even when you ask questions of this sort, it's perfectly fine to make pictures like this. And then this is what you, and then you just explain what's going on. Because that's perfectly fine. Okay, so what I had in mind today, and this is the same thing that I've asked your TA, James, to do, is work through some of all these sample problems here. There's going to be, again, the first question in the exam is going to ask about a definition, a theorem, or something that we have used in class, something we've talked about many times, like the mean value theorem. We used that a lot. Just the other day we used Rolle's theorem, something like that. And then there are a number of questions here. There's no way I can take you through all of them, but the first one I had in mind was this one here, number 10, because it gives us a little application of Taylor's theorem. So let me just show you how one could answer this. The solution does something else, but let me just show you what I had in mind. Right, so you take number 10. Take number 10. So you're looking at fn of x. We have a sequence of functions. So you have n(e) to the minus nx. And let's say x is positive. Then what we want to know is, you want to know what is the limit as n goes to infinity of n(e) to the minus nx. Well, it's the first thing that comes to mind is, well, this is a minus n here, right? So it's tempting just to write this here as the limit as n goes to infinity, and then you have n over e to the nx, right? And then you start using, and then use L'Hopital. Nothing wrong with this, is going to work out just fine. But given that we just talked about Taylor, given that we just talked about Taylor, we could write out what E and X is. So E and X is Taylor's formula, right? It says we have an infinite sum of what nx to the power k divided by k factorial. So if I look at the ratio I have to deal with, right, this is going to be n divided by e and x. So that's going to be this big sum. So if I divide by something smaller, for example, n, and then I take the second term in here. The second term would be so 0, 1. So you're going to get nx squared divided by 2. And so now you have it, right, because you have n upstairs and you have n squared downstairs. So this here is going to be, well, it'll be 1 divided by a half n x squared, right? And that thing is going to go to 0 as n goes to infinity. This example here is so the function that you have converted to 0. So what is interesting here is so this is just a note. Maybe at some point you wonder about this. All righty, Brian, you don't. There's something you don't like. What don't you like, Brian? Tell me. The Taylor series of the exponential function. Like so, e and x, the exponential function's Taylor series is given as what you have here. Like you take the exponent to the power k, right, and then you divide by k factorial. And so what we're using is that all these terms here, they're positive. So if I throw them away, right, this I could just pick one of them. So here I pick the second one. So I have nx squared divided by 2 factorial, so it would just be 2. So the exponential function is bigger than this thing. Like x is positive, which is so when I divide by something that is smaller, right, I'm going to get something that is bigger. So the little additional note that I wanted to highlight with this example is it's interesting if you integrate it. So if you integrate this function from 0 to infinity of n e to the minus nx, if you integrate this, you will get right, so what will be, it'll be get minus 1 over n down. So this is minus e to the nx, right? And then you have x being 0, x being infinity. So this is a 1. So it's interesting that if you take the limit as n goes to infinity of these integrals, they're always equal to 1. So a limit of 1s, this is going to give you a 1. But if you move the limit inside, right, then you're going to get the 0. This is equal to 0. So you have a limit outside an integral and you have a limit inside an integral, and these two things are not the same. 0 and 1 are not the same. So should you ever come across something called Fatou's lemma, Fatou, I cannot even spell Fatou. Fatou's lemma. This will help you understand why these two things, there's going to be, one is always bigger than or equal to the other, but there might be strict inequality. And there's a result called Fatou's lemma, and this here is like an example of a case where you have an inequality, a strict inequality in Fatou's lemma. This is just a side note. Sometimes we learned about limits now and we're starting to integrate. We could be interested in moving these limits in and outside the interval. And this example here shows that you really need to be careful about that. Okay. Are we all good on the first part of the solution here? Okay, so then the next one, there's going to be something about uniform continuity on the exam. So let's do, I had planned on going through a number of examples about uniform continuity. And some of them are easier than others. And I want to start out with one that's a little bit on the easier side. And the next one is this 12a. Let me bring up 12a. So 12a. So here we have a function. It's this cosine thing. And we want to know if it's uniformly continuous. So let me write down what the function is. So this is f of x. This is equal to 1 minus cosine. Everything is squared divided by log 1 plus sine to the power of 4, something like that. And then you have x's in 0 to 1. Okay. So we want to know if f is f uniform continuous. Uniform continuous. And it would have been so much easier if you would have had a compact interval. So what we want to use is that we have proven a result in class that says that so if it's continuous, that's good. So we have seen that if continuous plus a compact domain produce uniform continuity, right? We have seen a theorem like that. So here we have a continuous function, so that's good, but we don't have a compact domain. This domain here, this is open, it's not closed. It is bounded, however, so that's good, but it's not closed. So that's the obstacle we're facing in this example here. This is not closed. So if you want to answer a question like this one, what we can do is we can try to see if we can extend f to the closed interval 0 to 1, because if we can, then we can use this result here. Right, so we could try to extend f to 0 and 1. And if we can, in a continuous fashion, right, then we can use this result here. Then you're going to get uniform continuity on the closed interval. And of course, the closed interval is going to be bigger than the open interval. And then you have it. So the way to go about doing that is that we have to compute. So we need to take limits. So we're going to take two limits. And the first limit is going to be to consider the limit as x goes, one of them is easy, x up to 1, I think is the easy one, of f of x. So that one is the easier one because I'm just going to get, nothing here goes bad. I'm going to have sine of 1 here to the power 4. I have log of 1 plus sine 1 to the power 4, 1 minus cosine of 1 to the power 2. So this is good. This is fine. This is a number in R. So the troublesome one is, right, so that means I can close it up here. I can extend it up to and include the 0.1, but what about down here at 0? So then we also need the limit. I'll go downstairs of f of x. So now this is more complicated because what do I get downstairs? It just sine of 0 is 0. So I'm going to get log of 1. So that's a 0 downstairs. This is already trouble. And then upstairs, cosine of 0 is 1. So that's also a 0. So I have one of these situations, so I need to work. So we need to be more careful about when we pass x down to 0. And of course, again, we can just start multiplying, start taking derivatives and apply L'Hopital. We can also apply Taylor. Let me try something that's a little bit more elementary. Just try to simplify. So if I look at f of x according to this formula of here, what I can do is, I have a square. So I have 1 minus cosine here. But what I could do is I could divide by x squared. I then have a square and a square. I need a power 4 out there. And then downstairs, what I can do here is I can do log. I want to have 1 plus sine x to the power 4. And then I could divide by sine x to the power 4 and then multiply into sine x to the power 4. So I didn't do much, right? This stuff here will cancel and this one here will cancel, and I'm left with the original expression. And then the last thing I want to do is I want to move this square. I want to move the square down here. So let me put that square, no, that power 4, let me put it down here. 1 minus cosine of x divided by x squared to the power 2. Everything divided by, and then it's a log 1 plus sine x to the power 4 divided by sine x to the power 4. And then I have sine x to the power 4 divided by x to the power 4. So let's see if I can work out what all this stuff here is. Right, I have 3 terms. I do the limit as x goes to 0 of the top one, 1 minus cosine x divided by x squared. 0 over 0, I compute derivatives. I'll get that this is 2x downstairs. Cosine's derivative is minus sine, so I'm going to get sine x here. So this is again 0 over 0. So I'll use L'Hopital one more time. And then I'll get the derivative of sine is going to be cosine. And then over 2. So ultimately just give me a half. Right, so this term here, this is going to go to a half. And what about the other ones? Well, the other ones have 1 plus sine x to the power 4 divided by sine x to the power 4. So let me try to work that out. So if I take the limit, x goes to 0. Instead of sine x to the power 4, let me just write a t. Log 1 plus t divided by t. This is again 0 over 0, so I'll write it as a limit, not as x goes to 0, as t goes to 0. Right. So these are derivative. Downstairs we're going to get a 1. Upstairs we're going to get 1 over 1 plus t. T goes to 0, I'm going to get a 1. And then the last one is sine x over x to the power 4. So sine x over x, we've had that before. This just converts to 1. And so we put all these things together, we're going to see that this thing here converges to, it'll be, what will it be? It'll be a half squared and divided by 1 times 1. So we're going to get that it converges to a quarter. Okay, so what we have now is that this mess of a function, it does have limits, finite limits, as you converge to 0 and to 1. So there is a continuous extension. So f of x extends continuously to the closed and bounded interval. So f is uniformly continuous on this interval. And of course, in particular, it'll be uniformly continuous on a smaller one. Okay. Are there any questions on this part? We had a function that was defined on a bounded interval. And to check for uniform continuity, you can try to do this extension. Because if a function is uniformly continuous on a bigger interval, then it's also going to be uniformly continuous on the small one. How does that sound, guys? Can you follow? All right, then let's try something that is more tricky. This year was just there are more of these questions here. But let me try something in the same like spirit, but this is going to be harder. So let me try to make it a bit more complicated. This year was question A, right? So there are a few more to try, like there's a B and a C and so on. The one that I want to play with is harder. So this is this guy down here. This one here. F of x is this whatever nightmare of a function. So 15. Let me write out what the function is. F of x. This is e to the x. And then sine, and then inside sine, you have e to the minus x, sine x divided by x. I'm not going to give you something that is quite this crazy, but, and so now you have your x's between 0 and infinity. And again, x is continuous. And we want to know, is it uniformly continuous? And so this time, this is going to be harder because this interval here is not bounded and it's also not closed. So as before, we could try to at least get rid of the 0 down here. We could try to look at the limit as x goes to 0 of f of x. And I'm not going to work it out this time. I'm just going to plug in here that this is equal to 1. All right, so we can extend f to the closed interval 0 to infinity. But this is not bounded, right? So this is not bounded. It's closed, but it's not bounded. Right, so it's not compact. So we cannot use that result that says that if I have a continuous function and it's a compact set, then I have uniform continuity. So the problem now here is, is at infinity. It's out here. And so the first thing we could try to do is like, how does f behave out near infinity? Right, so we could compute. So let's compute the limit as x goes to plus infinity of f of x. Right, then I'm not going to fill in all the details here in the solution. You're going to get that this is equal to 0. So then, so there is a limit out here and it's equal to 0. So is that good enough? Is that good enough for uniform continuity? And right, so we have a function, it's continuous. It has a function that is continuous, and it has a 0 value out here in infinity. Is that good enough to get continuity? And we currently don't have any result about that in class. So the answer is yes. But this is not obvious. And the way to get at it is to backtrack a little bit. Right? We're working down here in question 15. And this hint here, this way of doing business, this could also be useful in exam settings. Like if you're stuck on something like this, try to go back and have a look at the previous problem. Okay, so what does the previous problem say? It says that if I have a continuous function, and I have another one, but the other one is uniformly continuous, and they have this property that they agree out at infinity, then that continuous function you had to begin with is uniformly continuous. So let's try to solve this problem and then see how to use it to solve this 15a problem. So we're going to switch and we're going to solve. So this is yes, and this here, we're going to get back to this yes here. This is to be filled in. So I'll leave a little bit of space here. Let's do problem number 14 first. So in 14, what we have is you have a function that goes from 0 to infinity. This one is continuous. Then you have another function that goes from 0 to infinity, and this one here is uniformly continuous. And you have a third property, namely that when I compute the limit as x goes to infinity of the difference, I get 0. Then the claim is that if I have such a setting, well then f is also uniformly continuous. And let's just see let's just see here that what kind of a function could I use? What kind of a function? So here what we have exactly in the previous problem, we have exactly a function. I have exactly a function that is that is continuous, and it has this limiting behavior here. So do we have a good G? Yeah, so yes, you can use number 14 with, what kind of a G could I use? Could use G just to be the zero function, right? Because that one is uniformly continuous, it's zero everywhere. And it has the right limit, and then it follows. So if I can prove 14, I can use it to resolve the question that I was stuck with before. So how does one prove 14? Well, you use the definition. This is always allowed. And what we know is, we know that G is uniformly continuous. Okay, so you let epsilon be given. Then what do we have? We have a uniform continuity property. We have a G here. G is uniformly continuous, so that means that there exists a delta 1, which is really a function of epsilon, such that whenever I keep x and y close, then I'm going to also have that the values over here, the values of G, you close, right? And so when you have uniform continuity, it's very important that this delta here does not depend upon x, it does not depend upon y, right? It just simply depends upon epsilon. So that's uniform continuity, so I'll give me that one. So that's this one here. That's this one that does that. What else do we have? We also have that property that converts to 0 as x goes to infinity. So what does that mean? Well, it means that there exists an L, again, a function of epsilon, and this is a big number, right, such that whenever I'm big, the difference is small. No, y is just next. That this is less than epsilon. So that's this one. That's the blue. That's the blue one. And then the last one we need is, if I look at the interval from 0 to L, say +1, that's where my f is. F lives all the way up to infinity, and that's continuous. So if I look at 0 to L +1, f is uniform continuous. Right, so because this is compact, and f was given to be continuous, so I take compactness, continuity, I'm going to get uniform continuity, the property we used to solve a problem just a little while ago. So I have now used all the properties. I used that G was uniform continuous, I used that f is continuous, and I used that it converges to 0 to create all this stuff here. So on this interval, f is uniform continuous, right? So that means that there exists a delta, let me call it delta 2, which again only depends upon epsilon, such that what? So if I keep x and y in that interval, 0 to L +1, you're going to see why it's L +1 and not L in just a second. Such that the distance is small, to be less than delta 2, then that's going to imply that the function values are close. What is left to prove now is that I have uniform continuity of f, not just on this interval 0 to 1, but all the way out to infinity. Okay, so how do we do that? We're going to set delta it's always our job, given this epsilon, right, it's our job to create a delta that works. And so we're going to set delta to be is always the min. We had a delta 1, we had a delta 2, and then I'm going to put in a half as well. And this half there has a lot to do with this +1 here. And now we just need to check that it works. Right, so let x and y be in the interval 0 to infinity. Let's say that d are less than delta. What we want to prove now is this delta here clearly does not depend upon x and it does not depend upon y. So what we want to prove now is that f of x is going to be close to f of y. Close in the sense that it's less than epsilon. Right, so then let's do some cases. The first case would be that, well, say x and y belong to the interval 0 to L plus 1. Well, if you belong to 0 to L plus 1, then I have it. Then I have it. So where else could you be? Well, they could also be big. They could be, it could be the case that you were, like you just given to be in 0 to infinity, so they could be big. They could be bigger than, say, L. So now I cannot necessarily use this anymore. And so what will I do is try something else. F of x minus f of y. That's the one I have to bound by epsilon. And the way I'm going to do it is this old trick that we've seen many times. I add subtract the same thing, f of x. Then I'll do minus g of x plus g of x minus f of y plus f of y. No, not f. It's this minus this one, so I have g of y and then minus g of y. And any guesses on what I'm going to use next? Almost always comes after I add and subtract the same thing. What comes after I add and subtract like this inside an absolute value? Right, we group the terms, and then what do we do? Does anybody want to say what would be the next step here? When I have fx minus gx plus gx minus fy plus gy minus gy. What would be the next thing to do? They're triangling the calls. Very nice, Alex. Okay, so I group them. I want to have f of x minus g of x. That was the first one. Then I want to have g of x minus g of y. And then I want to have f of y minus g of y. So let's see what we get then. This one here is good because g is uniformly continuous. It's this thing here. This is going to be less than epsilon. And what else do we have? To keep in mind the x and y's, they're big. X and y, they're big. So So I also have x and y are big, right? So the distance between f of x and g of x, that's going to be small because whenever x and y are big, this distance is less than epsilon. That's what I have here. So this one here is less than epsilon. This one here is less than epsilon. All in all, this is less than 3 epsilon. I'm good to go. So that took care of when x and y were small, then when x and y are big. And then, of course, you have cases in between. You'll have a case where x is small, and you'll have a case where y is big. But if that's the case, then the distance between x and y, this is going to be bigger than 1. But that's not possible, right? Because the starting assumption was that x and y had distance less than delta, and delta is less than 1/2. So this is not possible. I also could have that y is in between 0 and L, and x is bigger than L plus 1. Then I'll have the same thing, and this is not possible. Here delta is less than 1/2. And these are the cases that are there. And so in all cases, by keeping x and y close to each other, I'm gonna get that the f of x and f of y are close to each other, less than 3 epsilon. So this year shows that you indeed have like g of x is uniform. G of x being constant equals 0, right? That's going to be a uniform and continuous function. But there are other things in there as well. It doesn't just have to be the 0 function. You could also have functions that explode at infinity. You could have like an example. This is to use now here with to use for G. You could say G of x. If you take an affine function, a plus bx. This is uniformly continuous on the interval 0 to infinity. Siemens Lipschitz. We talked about Lipschitz. And how would you prove that such a function here is such a use for G above? So the one we used was just the 0, right? So then you have a and b constant equal to 0. But you could do a linear function as well, and let me just show you how one would do it. Right? If you looked at g of x minus g of y, and how bad would it be? Well, the a's will cancel, and you would have b outside, and then you have x minus y. Okay, so for epsilon bigger than 0, we could choose our delta to be say epsilon divided by 1 plus the absolute value of b. Then if I looked at x minus y being less than delta, then that's going to imply that g of x minus g of y is going to be equal to this thing we have here. Absolute value of b, x minus y. Now x and y are less than delta, right? So this is going to be less than b times delta. And delta was absolute value of b epsilon divided by 1 plus absolute value of b. And this here is less than epsilon. So you could use, it doesn't just have to be the zero function like we did in the example, you could also use an affine function. Right, an affine function is you go to plus infinity, right, and minus infinity depending on the sign of b. Okay, any questions on this part? So now we found another way to check and prove, figure out if you want, if a given function might be uniformly continuous when it's defined on the positive, axis. Any questions on this? Should we try another one? The next one I wanted to try was 15b. Bring it up. So 15b. We did 15a now. Okay, so that one was uniformly continuous. So now here we have 15b. This is x log x. And x is bigger than or equal to 1. Let's try that one. Right, and what the example just showed was that if this thing here had at most, if this could be bounded by a linear function, then we would be good to go. So is this bounded by an affine function? Because if it is, then we can use the previous material. Like, is it true that could we have that x log x minus a plus bx, that this would go to 0? What do you guys say? Alex says no. No. Why is that, Alex? Yeah, but bx is also unbounded. Right? This is true. This is unbounded, but this is also unbounded. Are you saying log? Yes, very nice, very nice. Good, good, good. Yes, sorry, I didn't see the full. I should pay closer attention to this chat. So what Alex is saying is this is not possible. So let's just check that. If I look at the limit as x goes to plus infinity of x log x divided by a plus bx, then you would end up with a limit as x goes to plus infinity of log x divided by b, right? And this is what Alex is saying, that this is plus infinity. Aha. Right, so the answer here is no. This is no. No. So is it uniformly continuous? Like here, we are in bigger problems, right? Because it's fine, like this x here. The bottom part is good, but it's unbounded up here. And the function is growing so fast that it exceeds this thing that we have proven we could potentially do. Any guesses on, do we have a conjecture on what we think is going to be true? Do we think that this is, uniformly continuous? Do we have a conjecture? But we wanted to see if I mean, could this converge to, could this go to zero? So we want to compare the growth of these two, right? And this one here just grows faster. So how do I measure that something grows faster? Well, I could look at the ratio. So that's what I did. X log x just grows a little teeny tiny bit faster than any linear function. What about this one? Is he, so we know he is uniformly continuous on 1 to L for any L. So this is okay, but he is not uniformly continuous on the interval 1 to infinity. And so we don't have any tool at this point, but Alex, you might have a sense. What do you think about functions that grow faster than these affine functions? Imagine you're sitting here and coming up with conjectures. What would you think? Alex is saying like, wild conjecture. If f is uniformly continuous on this interval, we're looking at, what was it, 1 to infinity. If f is uniformly continuous, then there exist constants a and b. They're going to be positive, such that f of x is bounded by a plus bx. Okay, in particular, x log x cannot be uniformly continuous. on this interval 1 to infinity. Okay, so this yeah. This is not if and only if, right? I'm saying that if f is uniformly continuous, then it must be bounded by a linear function, right? There's no if and only if here. This is not how it goes. So I'm saying that if it's uniformly continuous out at infinity, it cannot grow faster than linear. Right, and this one here does. So there's no way for it to be. Okay, so this is number 13. This is number 13. So let f be uniformly continuous. Now we want to construct A and B such that f of x is less than a plus bx for any x so how do we do this? The only thing we have to hang our hat on is this uniform continuity. So uniform continuity is what is it going to give us? So we can use it for any epsilon. So let's use it for epsilon equal to 1. Then what? We will have that if x and y, right, use this one, then we're going to get this delta such that x minus y, when this is small, we're going to have that the points f of y and f of x, they are close. And so I'm using here with epsilon equal to 1. That's the thing we have to hang our hat on. Okay. So first pick an n. First pick an n such that n is less than x divided by delta is less than n plus 1. Right, so x is a number, delta is this itty bitty teeny tiny small number here. So I can do this. So that's the first step. And then second, we're going to use the triangle inequality again, Alex. So there's going to be a mess coming up now. So second, we're interested in bounding this f of x. Yeah? We're going to create these constants. And the way we're going to do it is by using the triangle inequality. And this is always about adding and subtracting. So plus and minus. Then I'll do f of x minus delta. That's this delta here. Plus minus f of x minus 2 delta. Plus minus all the way up to the end, f of x plus minus f of x minus n delta. Right, so I'm adding, subtracting the same thing over and over and over. The only thing that happens is that I'm multiplying a bigger and bigger constant onto this delta. So this, of course, all happens inside the absolute value. So there's nothing, I didn't change anything. I'm adding and subtracting the same thing all over. And then we use a triangle inequality, as we just did. Give me a line. I'll keep the first, so this would be f of x minus, give me f of x, and then minus f of x minus delta. And then I'll do the next one. This will be f of x minus delta minus f of x minus 2 delta. And I'll keep doing this. Plus, plus, plus. The last one, I might want to have plus minus here, f of x, f of 0. I can do that all the way down to the end, f of x minus n delta minus f of 0 plus f of 0. Now, how big can the first one be? How big can the first one be? Well, let's just put equalities here. It doesn't matter. If I'm within delta range of each other, then the function value is going to be less than 1. Here I am within delta range of each other. So this is going to be a 1. This is going to be a 1. 1, 1, 1, 1, 1. And then absolute value of f of 0. I count them up. I hope I counted correctly. I get n plus 1 here. Plus, and then the absolute value of f of 0. And then I'll use that n is less than x over delta. Plus 1 plus the absolute value of f of 0. And this is my a. So my a was the constant coefficient. This was 1 plus the absolute value of f of 0. And let's stop here. I want to put a 0 here. And then b is 1 over delta. So Alex, your conjecture was right. The being uniformly continuous all the way out, it doesn't matter if it's 0 or 1 here. If you want to be uniformly continuous all the way out to infinity, it really imposes that your growth cannot be too much. It must be bounded. And as Aya points out, that is not sufficient, right? That is not sufficient. Like what Aya is saying, like if the oscillate out there, then it might fail. But that is really well aligned up with what we have here, Aya, right? Because like your function can be continuous and then it oscillates, right? If it oscillates, it's not going to have this property here. Right? A function that oscillates is not going to be, it's not going to have the property that it grows at exactly the same rate as this uniformly continuous function you have. Right, so this is a sufficient condition to be uniformly continuous. And over here, what we're saying is that if you're uniformly continuous, then you can grow no faster. You can grow no faster than an affine function. Right, and so here we have a function that grows faster. So there's no way it can be uniformly continuous. Are there any questions? Okay, this was all I had prepared for today. There are still lots of questions and problems on this sheet. Some of you have asked about how much we should prepare for Taylor and how much you should prepare for this differentiation under the integral sign. And I reserve the right to put something about that on the final exam. But here for the midterm, that's not going to be this material. This is not going to be there. I feel like you haven't had any homeworks on it, and I want to give you guys some time to think about it. But I'm not saying anything about the final. And the final is fair game. But the exam I drafted for Wednesday, it doesn't have anything about differentiation under the integral sign, and it doesn't have anything about Taylor. So I wouldn't spend my time doing that. But as you can imagine, given the amount of time that we spend today on uniform continuity, there's probably going to be something about uniform continuity in there. And the other thing is that for your first midterm, there was nothing about connectedness. So given that we spent the first time of today's lecture on connectedness, there's probably going to be something about connectedness on the midterm. Are there any questions? We have a few minutes left. There's also going to be something about derivatives. What I'm saying that like the last two topics we had this week on Monday and on Wednesday, namely the differentiation under the integral sign and the Taylor formula, how to compute limits for using Taylor formula. I didn't put anything about that on there on this midterm, but for those of you that are going to take the final, it might be there. All right, if there are no questions, then again, there are TA office hours on Monday, and then I'll have office hours on Tuesday. And if I won't see you before, then I'll see you on Wednesday. The difference between continuity and uniform continuity, I mean, like if to be uniform continuous, it is a very strong requirement. So for example, this function we had here at the very end, like this one, that one is continuous, but it's not uniform continuous. So a problem that we run into all the time is how do we, given a continuous function, how do you determine whether or not that continuous function is also uniformly continuous? And so we have some results now available. Like, so if you have a domain that is compact, then you're going to get uniform continuity. We've had examples in class in the very beginning that if your derivative was bounded uniformly, then you would get to be uniformly continuous. Now we had an example today about if you are an affine function, then you are, if you are an affine function, then you're uniformly continuous. So the class of uniformly continuous functions is much smaller. Is much smaller than the class of continuous functions. So you're not the same. But the general question, which is also I was getting at it, like, can you give me necessary and sufficient conditions for a function that is continuous to also be uniformly continuous? And the answer to that question is no, I cannot do that. It is that criteria of being uniformly continuous. It does not lend itself to that. Right? I can give you some sufficient conditions, and then I can also tell you some necessary conditions. Right? So today we had some new sufficient conditions, and one of the new sufficient conditions we had. Right, so we started out with an old sufficient condition. We started out with an old one that said that, like we have seen, if you have a compact domain and continuity, you're uniformly continuous. So that was an old one, right? And then we moved into uncharted territory. Like, what about if we start having a domain that is not compact, something like this? Then what do we do? What are sufficient conditions to ensure that you're uniformly continuous on this closed interval, but it's not bounded, right? So then it becomes a question. So here is a set of sufficient conditions. If your function that is continuous behaves like a uniformly continuous function out at infinity, then that function is also uniformly continuous, right? So that's a new set of sufficient conditions. For example, G here, which is uniformly continuous, that could be an affine function. It could be a function that has a bounded derivative, and so on. And then finally, we ran into this example with the x log x. There we turned it around a little bit and we said, okay, so what is, if you're uniformly continuous, what must then necessarily hold, right? So what are necessary conditions? Right, so I'm hoping everybody is good on the difference between sufficient and necessary, right? So if you're uniformly continuous, what must then necessarily be true? And what must necessarily be true is that you're bounded by an affine function. And of course, all the action here, it happens out at infinity, right? Because had this been a finite number, then you would just be bounded by a constant, because any continuous function on a compact interval is going to have a max and a min. And so you could just use A. Like the cool thing to look out for here is how fast f is allowed to grow out at infinity. And if you want it to be uniformly continuous out near infinity, it cannot grow faster than an affine function. Yeah, are there other questions? Otherwise, I will see you guys next week. Okay, I will see you next week.